short circuit or ground fault between phases or to ground could have created a high current surge that exceeded the fuse ratings. The fuses may have been defective or overloaded, preventing them from opening properly and allowing the fault current to continue. Loose connections could have created high resistance, leading to arcing and overheating of the fuses and wiring. Direct corrosion or physical damage could have compromised the fuse's integrity, affecting their ability to open reliably. The fuses used may not have had the correct capacity or interrupting rating for the circuit, allowing the fault current to damage the equipment. The fuses used may have been slow-blowing or not designed to handle the high fault current. The circuit may have been overloaded, exceeding the fuse ratings and preventing them from opening. Arcing or a short circuit between fuses or in the circuit could have bypassed the fuses, preventing them from opening. The main disconnect fuses are designed to protect the entire system from overcurrents and fault conditions. The high current surge from the heater fuse block could have overloaded the main disconnect fuses, causing them to open to isolate the fault. Firstly, carefully inspect the wiring downstream from the chart fuse block for any damage or insulation issues. Secondly, check the heater contactors for proper contact and ensure they are not sticking or welding closed. Thirdly, verify the system grounding is intact and properly sized to prevent ground faults from causing overcurrents. Inspect the immersion heaters and small motors for any signs of damage or overheating. Several factors can contribute to fuse failures in a 480 volt three-phase system, including high fault currents resulting from short circuits or ground faults. These high currents can surpass the fuse's capacity. Defective or overloaded fuses might not function as intended, allowing the fault current to persist. Loose connections can introduce high resistance, leading to arcing and heat buildup around fuses and wiring. Contamination, corrosion, or physical damage can also compromise fuse integrity, impacting their reliability. Additionally, incorrect fuse selection, such as using fuses with inadequate capacity or interrupting ratings, can lead to equipment damage during fault conditions. When fuses fail to open as expected, it could be due to several reasons. Incorrect fuse types, like slow-blowing fuses unsuitable for high fault currents, may not respond quickly enough. Overloading the circuit beyond the fuse's rating can also prevent them from opening. Arcing or short circuits occurring near or bypassing the fuses can also hinder their operation. The opening of main disconnect fuses upstream is typically a protective measure. These fuses safeguard the entire system against overcurrents and faults. A cascading fault, where a high current surge from a heater fuse block overloads the main disconnect fuses, can trigger their opening to isolate the fault and prevent further damage. To further investigate the cause of fuse failures, conduct a detailed inspection of the wiring downstream from the affected fuse block, looking for any signs of damage or insulation issues. Verify the condition of heater contactors, ensuring proper contact and the absence of sticking or welding. Confirm that the system grounding is intact and appropriately sized to manage ground faults effectively. Finally, examine the immersion heaters and small motors for any indications of damage or overheating that could contribute to the problem. High fault current occurs when there is a low resistance path for current to flow, usually due to a short circuit or ground fault. This leads to a rapid and significant increase in current flow. Fuses are designed to interrupt the circuit when the current exceeds their rated capacity, protecting equipment and preventing fires. If a fuse is defective or improperly sized, it may not trip quickly enough or at all, leading to damage. Loose connections create resistance, which generates heat. This heat can degrade the insulation of wires and components, leading to further failures. Over time, loose connections can also cause arcing, which is a dangerous electrical discharge that can ignite flammable materials. Contaminated or damaged fuses may not function properly, as their internal components can be affected by dirt, corrosion, or physical stress. This can alter their response time or prevent them from tripping altogether. Selecting the correct fuse type and rating is crucial for proper circuit protection. Fuses are available in various types, such as fast-acting and time delay, each designed for specific applications. Using the wrong type or a fuse with an insufficient interrupting rating can lead to catastrophic failures. Incorrect fuse types, such as slow-blowing fuses used in applications requiring fast interruption, may not respond quickly enough to prevent damage. Similarly, fuses with inadequate interrupting ratings may fail to clear high fault currents, leading to equipment damage and potential hazards. Overloading a circuit occurs when the connected load exceeds the circuit's capacity, causing the current to rise above the fuse's rating. This can lead to overheating of wires and components, increasing the risk of fire and equipment failure. Arcing or short circuits that bypass the fuses can prevent them from opening, as the fault current does not flow through the fuse. This can occur due to insulation breakdown, loose connections, or conductive materials bridging the fuse terminals. Main disconnect fuses are designed to protect the entire system from overcurrents and fault conditions. They are typically sized to handle the total load of the panel and are intended to isolate faults that occur downstream. A cascading fault occurs when a fault in one part of the system triggers a series of events that lead to the failure of other components. In this case, a high current surge from the heater fuse block could have overloaded the main disconnect fuses, causing them to open to isolate the fault and prevent further damage. Carefully inspecting the wiring downstream from the charged fuse block is essential to identify any hidden damage or insulation issues that could contribute to the problem. Look for signs of overheating, discoloration, or physical damage to the wires and their insulation. Check the heater contactors for proper contact and ensure they are not sticking or welding closed. Contactors are electromechanical switches that control the flow of current to the heaters. If the contacts are worn, damaged, or sticking, they can create resistance and generate heat, leading to fuse failures. Verifying the system grounding is intact and properly sized is crucial for preventing ground faults from causing overcurrents. A properly grounded system provides a low resistance path for fault currents to flow back to the source, allowing the fuses to trip quickly and safely. Inspecting the immersion heaters and small motors for any signs of damage or overheating is important to identify potential sources of the problem. Look for signs of insulation breakdown, corrosion, or mechanical damage that could contribute to electrical faults. To further elaborate on the potential causes, the high fault current, in particular, is a critical aspect to understand. The magnitude of the fault current is determined by the voltage of the system and the impedance of the fault path. In a 480-volt system, even a small reduction in impedance can lead to a significant increase in fault current. Therefore, identifying and eliminating any potential sources of low impedance paths is crucial for preventing fuse failures. This includes thoroughly inspecting wiring, connections, and equipment for any signs of damage or deterioration. Regarding fuse failures, it's important to note that fuses have a finite lifespan and can degrade over time due to thermal cycling, vibration, and exposure to environmental factors. Therefore, regular inspection and replacement of fuses, especially in critical applications, is recommended to ensure reliable protection. When inspecting connections, pay close attention to the tightness and condition of terminals, connectors, and splices. Loose connections can create resistance, which generates heat and leads to oxidation and corrosion. This, in turn, further increases resistance and can eventually lead to arcing and fuse failures. To mitigate this, use appropriate tightening torques and consider using corrosion inhibitors on connections exposed to harsh environments. Contamination and corrosion can significantly impact the performance of fuses. Dirt, dust, moisture, and corrosive substances can accumulate on fuse surfaces and internal components, leading to increased resistance, reduced insulation, and accelerated degradation. Regular cleaning and protection of fuses from environmental contaminants is essential for maintaining their reliability. When selecting fuses, it's important to consider not only the ampacity but also the interrupting rating, voltage rating, and time current characteristics. The interrupting rating indicates the maximum fault current that the fuse can safely interrupt without rupturing or causing damage. The voltage rating indicates the maximum voltage that the fuse can withstand without arcing or breakdown. The time current characteristics describe the fuse's response time to different levels of overcurrent. Using fuses with inappropriate ratings can lead to inadequate protection and potential hazards. The importance of selecting the correct fuse type cannot be overstated. Different types of fuses are designed for different applications and have different time current characteristics. For example, fast-acting fuses are designed to quickly interrupt short circuits, while time-delay fuses are designed to withstand temporary overloads, such as motor starting currents. Using the wrong fuse type can lead to nuisance tripping or inadequate protection. Circuit overloading is a common cause of fuse failures. Overloading occurs when the connected load exceeds the circuit's ampacity, causing the current to rise above the fuse's rating. This can lead to overheating of wires and components, increasing the risk of fire and equipment failure. To prevent overloading, it's important to accurately calculate the load requirements of the circuit and ensure that the wiring and fuses are appropriately sized. Arcing and short circuits that bypass the fuses can occur due to various factors, such as insulation breakdown, loose connections, or conductive materials bridging the fuse terminal. These conditions can create a low impedance path for current to flow, bypassing the fuse and preventing it from opening. To prevent these types of failures, it's important to regularly inspect wiring and equipment for any signs of damage or deterioration. The main disconnect fuses play a critical role in protecting the entire electrical system from overcurrents and fault conditions. They are typically located at the main service entrance and are designed to isolate faults that occur downstream. The proper sizing and selection of main disconnect fuses is essential for ensuring adequate protection of the entire system. A cascading fault can occur when a fault in one part of the system triggers a series of events that lead to the failure of other components. This can happen if the fault current is high enough to overload downstream fuses or equipment, causing them to fail. In this case, a high current surge from the heater fuse block could have overloaded the main disconnect fuses, causing them to open to isolate the fault and prevent further damage. When inspecting wiring downstream from the charged fuse block, pay close attention to the condition of the insulation connections and terminals. Look for signs of overheating, discoloration, or physical damage. Use appropriate test equipment to verify the integrity of the wiring and connections. When checking heater contactors, ensure that the contacts are clean, smooth, and properly aligned. Look for signs of wear, pitting, or corrosion. Use a contact resistance meter to verify the integrity of the contact. Ensure that the contactor is properly sized for the load and that the operating voltage is within the specified range. Verifying the system grounding is intact and properly sized is essential for preventing ground faults from causing overcurrents. Use a ground resistance tester to measure the resistance of the grounding system. Ensure that the grounding conductors are properly connected to ground rods, metal water pipes, or other approved grounding electrodes. When inspecting immersion heaters and small motors, look for signs of overheating, insulation breakdown, or mechanical damage. Use an insulation resistance tester to measure the insulation resistance of the windings. Ensure that the heaters and motors are properly sized for the load and that the operating voltage is within the specified range. Consider the ambient temperature and ventilation when evaluating the condition of electrical equipment. High ambient temperatures can accelerate the degradation of insulation and other components, while inadequate ventilation can lead to overheating. Regular maintenance and inspection of electrical equipment is essential for preventing failures and ensuring safe operation. This includes cleaning, lubricating, tightening connections, and testing components. Keep accurate records of maintenance activities and inspections to track the condition of equipment and identify potential problems before they lead to failures. Moreover, consider the impact of harmonics on the system. Nonlinear loads, such as variable frequency drives and electronic ballasts, can generate harmonic currents that can overload neutral conductors, overheat transformers, and cause fuse failures. Use harmonic filters or other mitigation techniques to reduce the impact of harmonics on the system. The selection of fuses should also consider the application's specific requirements. For instance, motor circuits often require time delay fuses to accommodate the inrush current during startup. Semiconductor circuits may require fast-acting fuses to protect sensitive components from overcurrents. The fuse's interrupting rating must also be sufficient to handle the maximum available fault current at the installation location. Regularly inspect electrical panels for signs of overheating, corrosion, and loose connections. Thermal imaging can be a valuable tool for identifying hot spots that indicate potential problems. Tighten loose connections, replace corroded components, and clean away any debris that could contribute to overheating or insulation breakdown. Consider the environmental conditions in which the electrical equipment operates. Moisture, dust, and corrosive substances can accelerate the degradation of electrical components and increase the risk of failures. Protect equipment from these elements and implement regular cleaning and maintenance procedures to minimize their impact. Electrical safety is paramount when working with electrical systems. Always de-energize circuits before performing any work, and use appropriate personal protective equipment such as gloves, safety glasses, and insulated tools. Follow lockout/tagout procedures to prevent accidental energization of circuits during maintenance or repair. Implement a comprehensive electrical safety program that includes regular training, hazard assessments, and safe work practices. Ensure that all personnel working on electrical systems are qualified and competent to perform their tasks safely. When troubleshooting electrical problems, use a systematic approach to identify the root cause of the issue. Start by gathering information about the symptoms, operating conditions, and history of the equipment. Use appropriate test equipment to measure voltage, current, resistance, and other parameters. Analyze the data to identify potential causes and narrow down the scope of the investigation. Document all findings and corrective actions to facilitate future troubleshooting and maintenance. Finally, remember that electrical systems are complex and potentially hazardous. If you are not qualified or comfortable working on electrical equipment, seek the assistance of a qualified electrician or electrical engineer. Ignoring potential electrical problems can lead to serious consequences, including equipment damage, injuries, and even fatalities. A proactive approach to electrical safety and maintenance is essential for ensuring the reliable and safe operation of electrical systems.